Solve exercise 1, page 311 from Everest. In this experiment, its title is Determination of the Wavelength of a Monochromatic Light. The adjacent figure represents Young's double slit experiment. We have laser beam striking an opaque card which consists of or contains two slits S1 and S2, and here we have a screen E at 2 meters away from the card. The distance between the slits, I'm going to call it A, is 0.75 millimeters, and the distance between the slit and the screen is 2 meters. Okay, you can notice on the diagram that we have a screen an interference pattern of width 12 millimeters. In this pattern, we have 7 bright fringes. Bright fringe here, another one, another one, another one. Okay, we have 7 bright fringes. Let's read the question. A laser source S, this is the laser source S. A laser source S illuminates the two slits S1 and S2 at normal incidence. By normal incidence, we mean that the angle between the beam and the card is 90 degrees. This is what's meant by normal incidence. By a monochromatic light of wavelength lambda. So the wavelength of this radiation is constant. Therefore, the frequency is constant. Accordingly, S1 and S2 emits 2 waves of constant frequency. Therefore, they are synchronous. Part A. He is asking you, the light which falls on the 2 slits is synchronous and coherent. Why? Of course, the light originating from a laser beam is always synchronous, that is, has constant frequency or constant wavelength, and always coherent, because at any instant the phase difference between any two waves is constant. So we can say that in part A, since the lights falling on the 2 slits originates from the laser source. This means that the light is synchronous and coherent, as I've said before. Part B. Use the figure to part 1. Describe the phenomenon observed on the screen. Okay, on the screen we will observe alternative bright and dark fringes, that is, bright fringe, dark fringe, bright fringe, dark fringe, bright fringe, dark fringe, and from the other side, bright fringe, dark fringe, bright, dark, bright, dark. This is what do we mean by alternative bright and dark fringes, parallel to each other and to the slits. That is, if the slit is vertical, this fringe, the bright fringe, is vertical too, and the dark fringe is vertical too. They are parallel to the slits, and the fringes are rectilinear bands. Okay, rectilinear, and their centers are also equidistant. That is, the distance from the center of this bright fringe to the center of this bright fringe is equal to the distance from the center of this bright fringe to the center of that bright fringe. This is what I mean by the centers of bright fringes, or dark fringes for sure, are equidistant. I'm going to write my answer here. So we observe alternative or alternate alternate bright and dark fringes parallel to each other and parallel to the slits. The fringes are also rectilinear bands and their centers are equidistant. Part B2, determine the interfringe distance I. Good. The interfringe distance I is the distance between two consecutive fringes. That is, if this is my bright fringe here and this is my bright fringe, these guys are two consecutive bright fringes. This distance I is called the interfringe distance. From geometry, you can notice that the distance from this guy to this one is 12 millimeters. 12 millimeters. It contains how many eyes here? This is the first eye, the second one, third, fourth, fifth, sixth eye. Therefore, from geometry, the 12 millimeters contains 6 interfringe distances. This implies that I equals 12 over 6, that is 2 millimeters. Hence, I is 2 millimeters from geometry. Part C, deduce the wavelength lambda. Deduce lambda. In the course, we said that I equals lambda d over a. Lambda, we are given lambda, we determine it in part B2. This implies that I was 2 millimeters from part 2, therefore lambda equal I times A divided by D. So 2 times 10 to the minus 3 meters, times A, which is 0.75 millimeters. I have to convert it into meters, so sorry, divided by 2 meters, and I get my answer as 750 times 10 to the minus 9 meters, or lambda equals 750 nanometers.